Welcome to the deep dive. So, in just the last 14 days, the volume of inference compute across the global machine learning ecosystem officially surpassed the total volume of training compute.
Yeah, it's a massive milestone. The era of the token subsidy is just, well, it's dead.
Completely dead. And the structural economics of our entire field have basically inverted.
Yeah.
So we are looking at the window from June 7th to June 21st, 2026, and the velocity of these past 2 weeks has been just staggering.
Oh, absolutely. It's been a wild 2 weeks.
Right. And our mission here is to sort of cut through that noise. If you are a data scientist tuning a retrieval pipeline or, an engineer deploying some agentic framework, the underlying assumptions of your tech stack just shifted dramatically. So we want to synthesize exactly why these developments matter for your own deployment strategies.
Exactly. Because the inflection point we're looking at is really rooted in the collapse of the artificial pricing structures that kind of define the last 2 years.
Yeah, that venture-backed bubble.
Right, exactly. We saw Google trigger this whole collapse by threatening that aggressive 80% price cut on API token access.
Which is huge. It's like the early days of ride-sharing subsidies evaporating, right?
That's a perfect analogy, yeah. That move just effectively eviscerated the business models of countless AI wrappers, and it forced a really harsh reality onto the infrastructure layer.
Because you can't just compete on venture-backed discounts anymore.
No, you can't. When the hyperscalers decide to weaponize their compute scale, you can no longer compete on price abstraction. You are forced to compete on pure, bare metal architectural efficiency.
And the data backing this up is just undeniable. I mean, Infinigence, they run that agentic model as a service platform. They just published their internal metrics.
This 20x surge.
Yes, a 20x surge in token call volume over the past 6 months. And since they operate as a neutral translation layer between the raw silicon and the models, seeing that kind of surge in that specific middleware layer.
It means the volume of automated machine-to-machine token generation is skyrocketing.
Exactly. It is not humans typing into chatbots anymore. It's automated agentic loops running continuously in the background.
Right, and the technical implication of a 20x surge in call volume is a proportional explosion in KV cache pressure.
Oh, for sure.
So if inference compute spend is now your dominant line item, your optimization priorities as an ML practitioner, they have to pivot. Shaving 50 milliseconds off your time to first token is no longer just like a micro-optimization for a cool blog post.
Right, it's survival.
Yes, it is the core determinant of whether your deployed model operates at a positive margin or bleeds capital with every single API call. And the research out of the major labs over the past 14 days perfectly reflects this panic.
The focus has aggressively shifted from scaling the parameter count to scaling the throughput. And honestly, that compute pressure is the exact lens through which we need to view the current capitalization of frontier models.
Because the ability to secure the energy in silicon is dictating everything right now.
Exactly. And nothing highlighted this reality more than the funding shockwave DeepSeek sent through the market this week. They closed a $7.4 billion Series A.
Roughly 51 billion yuan.
Right, yeah. Valuing them at a staggering 400 billion yuan. But the valuation isn't even the most critical data point here, is it?
No, it's the structure of the cap table. Liang structured the round with 0 voting rights for the investors.
0. That's just wild.
Retaining absolute control at a 400 billion yuan valuation is virtually unprecedented, but it signals a really rigid commitment to pursuing AGI without commercial board interference. But honestly, the composition of the syndicate is what we really need to look at.
Yeah, because Tencent led with a 10 billion yuan injection, which, aligns with their ecosystem strategy. But the crossover investment from CATL.
That is the defining signal of this round.
Right. CATL and entering the frontier AI space is a massive structural indicator. We are looking at the world's dominant battery and energy storage manufacturer crossing over into deep learning infrastructure.
Which highlights the reality of the gigawatt data center. The bottleneck for inference at a global scale is no longer just the TSMC foundry yield rates for GPUs.
It's the physical grid capacity. You have to power and cool those massive clusters.
Exactly. CATL's involvement suggests a direct architectural integration between energy storage grids and compute clusters just to manage the massive fluctuating power draws of these trillion-parameter inference deployments.
And it's fascinating because while CATL and Tencent aggressively moved in, Alibaba and ByteDance entirely abstained from the round.
Yeah, they sat it out completely.
Which, impartially speaking, indicates highly divergent strategies regarding open weights versus proprietary APIs within the Chinese tech ecosystem. The companies sitting out are likely doubling down on their internal models, banking on their existing cloud advantages.
And this highly capitalized, highly fragmented ecosystem is just accelerating the technical timelines way beyond what people previously thought.
Oh, the acceleration is so visible in the public forecasting disputes we saw this week. Elon Musk projected on X that Chinese LLMs would reach absolute frontier capabilities by Q1 of 2027.
And Tang Ji, the CEO of Zhipu AI, immediately pushed back on that.
Yeah, he basically said the timeline is significantly shorter than that. And looking at the empirical benchmark data from the last 2 weeks, he might have a point.
Well, Zhipu AI's release of GLM 5.2 provided some really concrete proof. The model immediately claimed the first-place position on Design Arena's HTML web design benchmark.
Displacing Claude Fable 5.
Exactly. And if you analyze the telemetry from that benchmark, GLM 5.2 didn't just, generate syntactically correct HTML. It demonstrated a fundamentally superior semantic understanding of the document object model tree and third-party library dependencies.
So it wasn't just brute forcing the design.
No, it was efficiently utilizing existing ecosystem abstractions.
Wow. We also saw Tencent's Yuanbao model achieve a perfect 150 out of 150 on the 2026 Gaokao math exam, which is crazy because the Gaokao requires rigorous multi-step logical deduction without any intermediate reward signals.
A perfect score implies the model's internal search tree for theorem proving is highly optimized. It's effectively managing that exploration-exploitation trade-off without degrading into hallucinatory math errors.
But wait, this brings me to a severe contradiction that I want to ask you about.
Yeah.
If inference is now the dominant cost, and these models are hitting perfection on standardized tests like the Gaokao, aren't we hitting a wall?
A wall in what sense?
In the sense that hardware bottlenecks kill the ROI. Like, a flawless mathematical derivation is commercially useless if the compute required to generate it exceeds the value of the actual answer.
That contradiction is exactly why ML engineers have spent the last 14 days literally rewriting the rulebook on inference optimization. To survive the token explosion, you have to rewrite the rules of data movement.
Right, which brings us to the infrastructure layer.
Yes. The most significant breakthrough here is the June 17th update regarding the deployment of Ling 2.61T on TPU v7X hardware via the SGLang JX framework.
Okay, so let's break that down for the listener. What is the core problem with deploying a trillion-parameter mixture of experts architecture across a distributed TPU cluster?
It exposes the fundamental flaw of MOE routing. The computational efficiency of MOE is great. You only activate a subset of the parameters for any given token, but the network latency is just catastrophic.
Because of the data movement.
Exactly. When the router assigns a token to an expert residing on a different TPU pod, you trigger a massive all-to-all communication phase across the interconnects.
And the tensor cores are just sitting there completely idle while the tokens are shuttled across the network.
Yes, wasting expensive compute time. So the SGLang JX team solved this by writing a highly specific Palace kernel.
And Palace allows for custom kernel authoring directly for the PPU, right?
Right. And the breakthrough isn't just optimizing the math. It is overlapping the direct memory access transfers with the matrix multiplications. The kernel effectively hides the data movement latency entirely.
That is so clever. So basically, while the TPU is crunching the math for the current tokens, it's simultaneously pulling the next tokens over the network.
Exactly. Tightly coupling the memory prefetching with the compute pipeline. The network communication occurs entirely within the shadow of the computation phase. For an ML engineer, this proves that optimizing asynchronous memory operations yields way higher throughput gains than algorithmic tweaking at the model level.
That makes total sense. But beyond data movement, we are also hitting the physical limits of memory capacity, which leads us to that critical new ArcSviv paper on FP4 pre-training.
Rethinking shrinkage bias in LLM FP4 pre-training.
Yes. Pre-training in pure 4-bit floating point precision has been the holy grail for scaling laws because it slashes the required VRAM. But historically, it destroys the gradient fidelity.
And that degradation stems from the severe limitation of the representational space. In FP4, you only have 16 discrete bins to represent a value.
Right.
The paper mathematically formalizes a phenomenon they call shrinkage bias. During backpropagation, as the gradients are calculated and applied to the weights, the inherent quantization function forces the updated values to collapse geometrically toward the zero bin.
Because the scale of the gradients in deep layers is so tiny.
Exactly. Rounding them to the nearest available FT4 bin effectively zeroes them out. The model physically cannot update its parameters, so the learning process just stalls.
It's a systemic loss of signal. So how do data scientists fix this? The paper proposes the UFP4 recipe, right?
Yes, UFP4. The standard approach to quantization relies on static scaling factors, but UFP4 introduces a dynamic scaling mechanism. It continuously adjusts the distribution of those representational bins across the layers during the backprop pass.
So it modifies the clipping thresholds on the fly.
On the fly, yes. It dynamically recenters the quantization bins to capture the specific statistical distribution of the gradients at each layer. It prevents that geometric collapse by ensuring the active gradient values always fall within a highly resolved subset of those 16 bins.
Wow. So it preserves the gradient trajectory without actually expanding the memory footprint.
Yeah.
That is a massive systemic fix to look into.
It really is. Now, shifting to inference speed, we also saw a massive leap via speculative decoding.
Oh, a Spec V2. I love this one. So speculative decoding traditionally relies on a small, fast draft model generating candidate tokens, which are then verified in parallel by the large, slow target model. It's like predictive text on steroids.
Right, but the bottleneck has always been the acceptance rate. If the target model rejects the draft tokens, you waste all that compute and fall back to standard autoregressive generation.
Right, which defeats the whole purpose.
Exactly. But the release of the Spec V2 engine by Modal, ZLab, and SGLang fundamentally alters the mathematics of that verification phase. Historically, verification demanded strict alignment between the draft token and the target model's probability distribution.
But Spec V2 changes the acceptance criteria mathematically, right?
Yes. It introduces a generalized acceptance criterion based on bounding the total variation distance between the two distributions. By relaxing those strict token matching constraints, Spec V2 can accept sequences of tokens if the joint probability bound satisfies the threshold, even if the individual token probabilities diverge slightly.
Oh, I see. So it extracts utility from draft models that correctly predict the semantic trajectory of the sentence, but maybe pick a slightly different intermediate word.
Precisely. You achieve a significantly higher acceptance rate using a much smaller, less capable draft model. It drives down latency and costs simultaneously.
That is brilliant, and all these software-level optimizations are crucial, but they really have to interface with the evolving silicon landscape.
Which brings us to more threads.
Yes. A major domestic Chinese GPU manufacturer. They just reported 1.5 billion RMB in projected 2025 revenue. That's a 243% year-over-year growth. But, like we know, hardware volume is irrelevant without software integration.
And the defining event for this ecosystem was the SGLang and MUSA meetup on June 20th. MUSA is More Threads' proprietary compute architecture.
Designed to compete directly with NVIDIA's CD.
Exactly. And the milestone achieved at that meetup was merging the native MUSA backend directly into the SGLang mainline repository. Previously, running advanced inference frameworks on these GPUs required really brittle translation layers,
which totally degraded performance. But native integration means that the kernel-level optimizations we just discussed, like the asynchronous memory operations and the UFP4 quantization, can be compiled directly for the MUSA architecture.
Right. It marks the arrival of native GPU support in China's open-source AI ecosystem, bypassing the CDA dependency entirely.
Okay, so taking a breath here. Now that the infrastructure layer is operating at this unprecedented efficiency, the models can essentially be left to think longer.
Which unlocks the next massive transition, the era of loop engineering.
Yes. This is a provocative concept from recent industry analysis, the death of prompt engineering.
Because prompting implies a static, stateless interaction. You provide an input, you get an output, the execution ends. But developers are shifting from manually instructing AI to designing self-sustaining systems.
Right. Loop engineering is the architectural design of persistent self-correcting state machines. The model enters a continuous while loop. It observes, reasons, executes a tool, updates its state, and iterates.
But managing that continuous state without the model degrading into hallucinatory loops requires rigorous structural constraints, which is the exact focus of the Ledger Agent framework published just days ago.
Because the failure mode of long-horizon agents is state drift, right? By the 50th iteration, the context window is saturated, and the agent starts hallucinating tool availability. It assumes a file was written when the operation actually failed.
Exactly. Ledger Agent mitigates that state drift by introducing an immutable external ledger. The agent is not permitted to rely on its internal context window to track the state of the world.
Oh, that's smart. So every successful API response is written to this external ledger.
Yes. The framework enforces a strict policy alignment constraint. Before the agent can execute its next action, the system mathematically verifies the proposed action against the current state of the ledger.
It's like a pre-flight checklist. If the agent tries to modify a database but the ledger shows the connection failed earlier, the framework blocks it.
And forces the agent to resolve the dependency first. It prevents the compounding errors that destroy long-term autonomy.
But maintaining these loops burns through context windows rapidly, which drives up those inference costs again.
Which is where Microsoft's fast context architecture becomes critical, specifically for coding agents exploring massive repositories.
Right, because passing thousands of lines of irrelevant code into the reasoning model is just economically unviable. So fast context separates repository exploration from code solving, right?
Yeah. Exactly. It functions very much like a CPU memory hierarchy. They deploy a highly specialized, lightweight exploration model that acts as an L1 cache prefetcher.
So it navigates the file system and extracts only the relevant snippets, compressing them into a context vector.
And then the large, expensive reasoning model is only invoked once that highly targeted context is compiled. It drastically reduces token consumption, which directly solves the cost issues we talked about at the start of the deep dive.
That is huge. And when you are building these complex loops, you also have to architect a memory system. We saw two distinct philosophies emerge this week: Evermemos and Memento.
Yeah, two very different architectural approaches. Evermemos treats memory management as an operating system level process. It runs a continuous background daemon that processes dialogue streams into structured memory cells, doing active garbage collection on redundant context.
Okay, and what about Memento?
Memento bypasses the continuous compilation and the heavy compute overhead of traditional hybrid semantic graphs. It uses a typed semantic memory schema with information theoretic retrieval.
Information theoretic. How does that work in practice?
Well, historically, querying long-term memory required calculating cosine similarity across massive dimensional spaces. Memento categorizes data distinctly upon ingestion, like this is a user preference, this is a transient state variable.
Right.
When the agent queries memory, Memento calculates the Shannon entropy of the current state and retrieves only the specific typed memories that maximize the information gain.
Oh, wow. So it mathematically defines what data will reduce the uncertainty of the agent's current state, avoiding brute force similarity search entirely. That would drastically reduce latency.
Exactly. But designing these intricate memory schemas exposes a massive vulnerability. How do you rigorously benchmark an agent operating in a continuous loop? Standard tests like SWE-bench are kind of breaking down.
Right, because they evaluate static zero-shot generation, not a multi-step environment. That is the exact gap Gamecraft Bench attempts to fill. Can an agent build a playable game end-to-end within a real physics engine like Unity or Godot?
Yes, it tests practical engine grounding. The agent has to write code, parse error logs, adjust meshes.
It's testing persistent loop execution. But while Gamecraft tests execution, RNG Bench provides the mathematical rigor to diagnose agentic failure in non-Markov games.
And this is a crucial advanced concept. In a standard Markov decision process, the current state observation contains all necessary information to determine the optimal policy. The past is irrelevant, but real-world tasks are inherently non-Markovian.
Right. The data you need to make a decision right now might have been observed 50 steps ago and is currently hidden. So models have to reconstruct past observations.
Exactly. And RNG Bench introduces the memory gap metric. When an agent fails, did it fail to retrieve the data, or did it retrieve it but make a poor logical deduction?
The memory gap metric mathematically isolates that failure mode. It forces the model to explicitly reconstruct past hidden states before acting.
So data scientists can definitively partition the error. If the state reconstruction is inaccurate, it's a retrieval failure. If the reconstruction is perfect but the action is wrong, it's a reasoning failure. It's an absolute diagnostic X-ray for loop engineering.
That is so powerful. Okay, so once agents can reliably maintain memory and execute complex software loops, the next logical frontier is deploying that reasoning into the physical three-dimensional world.
Yes, physical AI. Over the last 14 days, the development of native world model stacks has accelerated dramatically.
Starting with Kairos, this is a new native world model stack engineered specifically for physical AI.
Right, because when a robot navigates a room, the streaming sensor data is continuous and highly redundant. Standard transformer attention scales quadratically, so it chokes on continuous high frame rate data.
But Kairos implements hybrid temporal attention mechanisms. It calculates the delta between frames and focuses compute exclusively on the elements that are dynamically changing.
Which allows it to maintain persistent states across different hardware platforms, even when sensors are occluded.
And NVIDIA addressed this from a different angle with Cosmos 3, their omnimodal world model.
Cosmos 3 doesn't treat vision, audio, and robotic kinematics as separate pipelines. It uses a unified mixture of transformers architecture that maps all modalities into a single, continuous, latent space.
Meaning the physical torque required to move a robotic arm and the visual representation of that arm moving are mathematically adjacent tokens. The model inherently understands causal links.
It eliminates the need for brittle translation scripts. But even with that understanding, the AI still needs a precise action interface, which brings us to Spatial Claw.
I love the ingenuity of Spatial Claw. It's a training-free framework that uses code as an action interface for spatial reasoning.
Right. Traditionally, you need massive data sets of human teleoperated trajectories to train a vision language model for robotics. Spatial Claw bypasses that. It prompts the model to act as a spatial geometrician, outputting a Python script that calculates 3D coordinates and bounding boxes.
It translates complex 4D spatial reasoning into a coding problem that LLMs already excel at. It's zero-shot physical manipulation.
And that structural efficiency is mirrored in ImageWham, a fascinating study out of Shanghai Jiao Tong University. It questions whether world action models actually need computationally expensive video generation.
Right, because generating 60 frames of predictive video to figure out how to move a cup is just exorbitant.
Exactly. ImageWham proves that pre-trained image editing models can effectively replace video generation. Instead of a continuous video, the model takes the initial visual state and simply edits that single image to reflect the target state.
Like in-painting the cup onto the target location. And then it calculates the visual delta and passes it to an inverse kinematic solver. That drastically reduces the compute required.
By orders of magnitude.
But I have to push back here. If Spatial Claw is just outputting Python coordinates and ImageWham is just applying diffusion in-painting to a 2D image array, are these models actually understanding physics, or are they just highly sophisticated statistical mimics tricking us?
That is the exact philosophical boundary we are navigating. But the S-Agent framework, recently published by Repedia, addresses this critique perfectly by focusing on temporal memory grounding.
Okay, how does S-Agent prove it's moving beyond pixel mimicry?
By forcing the vision language model to maintain an explicit temporal memory map. As the robot navigates, it continuously updates a persistent internal representation of the environment. Crucially, this grants the agent object permanence.
Oh, right. So if you put a barrier in front of an object, a purely statistical model might think the object ceased to exist because the pixels are gone.
But the S-Agent updates its temporal memory to register that the 3D object still occupies a specific coordinate vector hidden behind the barrier. Maintaining that persistent, unseen state is the foundational definition of understanding physical reality.
That is incredible. And bringing all these theoretical and infrastructural advances down to earth, let's conclude by examining what these tools have actually achieved in the wild over the last 14 days. Novel applied ML use cases.
The deployments are spanning from planetary macro systems to cellular microenvironments.
Starting with meteorology. A China-led team has developed an AI system specifically to track radar-disrupting space hurricanes in the upper atmosphere.
These are massive masses of plasma driven by solar wind. They are inherently chaotic and exceptionally difficult to model with traditional fluid dynamics.
But the deep learning architecture ingests massive streams of multi-instrument satellite telemetry to identify latent topological patterns and predict their trajectories,
allowing for proactive routing of satellites to avoid signal degradation.
And closer to the surface, the Hong Kong Observatory deployed a new model using machine learning algorithms to vastly improve the forecast accuracy for super typhoons.
It replaces heuristic-heavy statistical models with deep neural networks capable of processing high-resolution atmospheric data in real time,
providing much earlier evacuation warnings. Now, transitioning to biotech and healthcare, we saw the return of Cancer on a Chip pioneer Chen Weikang to China from NYU.
This signals a massive merging of physical microfluidics with AI analysis. You seed these chips with patient-specific cancer cells, and autonomous AI agents continuously monitor the cellular responses via computer vision,
iteratively adjusting the chemical compounds being pumped into the chip using reinforcement learning to discover highly optimized drug cocktails. It's the agentic loops we discussed earlier, applied to biology.
Exactly. And in the clinical diagnostic space, Google Research published new telemetry on AIE. It's not a narrow classifier. It's a long-horizon diagnostic co-pilot that conducts complex, multi-turn clinical interviews.
It updates its internal hypothesis state based on physician feedback. And shifting to finance, we have Agent FinVQA, a deployable multi-agent pipeline specifically designed for auditable financial chart QA.
Financial data is notoriously difficult for standard LLMs. Agent FinVQA utilizes the exact ledger agent architecture we dissected earlier. It deploys a team of specialized agents exploration, visual, and reasoning.
And every step is written to an immutable ledger, ensuring an audible trail of reasoning, eliminating hallucination risk.
Finally, to synthesize edge inference, physical AI, and chaotic environments, researchers successfully deployed the world's first smart squid fishing robot in the open ocean.
It sounds niche, but the engineering is bonkers.
Yeah.
It operates on the edge on a violently swaying vessel, utilizing real-time computer vision to penetrate the water, correct for light refraction, and calculate intercept trajectories for the squid.
Continuously updating its spatial targeting based on wave dynamics, it perfectly illustrates the convergence of everything we've discussed: edge inference, physical AI, and agentic loops.
It really is the ultimate synthesis. So, summarizing this absolute whirlwind of the last 14 days, whether you are optimizing a retrieval pipeline, trying to squeeze a model onto a smaller GPU, or building an autonomous agent, the mandate has shifted. The shift from training scale to inference efficiency and loop engineering is the new reality.
And as you build within this new paradigm, I want to leave you with a final provocative thought.
Let's hear it.
We are mathematically isolating failure modes with tools like RNG Bench. We are forcing models to validate actions against immutable ledgers. We are granting them temporal memory. The limiting factor in AI is rapidly ceasing to be the parameter count or the hardware bandwidth.
So what is the bottleneck?
The human's ability to accurately define the objective function. If an agent can recursively improve its own code, manage its own state, and operate in a non-Markovian world, what is your role as a data scientist in 2027? Are you still a model builder, or have you become a behavioral psychologist for synthetic minds?
Wow, behavioral psychologists for synthetic minds. That is the exact reality we are architecting right now. Well, that concludes our deep dive for this week. Keep pushing the boundaries of your infrastructure, keep questioning the math behind the architectures, and keep diving deep into the data. We'll see you next time.